is Martin from ME Drive Services. Welcome to our next video, where we will talk about asynchronous machine and specifically the torque characteristic of a fixed speed asynchronous machine. I'm sure you know that most of the industrial applications, industrial motor drives are using asynchronous machines, and very important is this torque speed characteristic. This formula is still not very complicated, it's relatively simple, just with few variables, kind of linear relationship, but still there is even a simpler way how to abbreviate the torque as a function of speed. So as you can see, it's abbreviated from the power and angular speed, and then substituting the expressions, putting rotor resistance into the formula, the stator voltage, the stray reactance, and the slip. This formula is still not very complicated. It's linear. It just has few parameters. I had an excellent teacher at the university, one of the best from my studies, and he once said that it does not matter how great you can solve complicated integrals and derivations and other mathematical calculus. If you start in your first job after the studies and you will not be able to explain why asynchronous machine is rotating, the other colleagues, they will not consider you very seriously. So I would like to give his message further and explain the torque characteristic as a function of speed, respectively as a function of slip, in a simple way, without heavy mathematics, and really focusing on your own understanding of it. This is the well-known characteristic of DOL asynchronous motor. DOL stands for direct online. So this is a fixed speed motor that is supplied from a grid with fixed frequency, typically 50 or 60 Hz, depending on the country where the motor is installed. Let's come to the characteristics. We see two quantities in the figure. One of them is the torque. This is the full line, this kind of shape. And the other one is the stator current, shown with the dashed line. Both of them are depicted as a function of speed. I'm using actually the relative speed, n over ns. This is how it's typically shown in the figures. The advantage is that this is generally valid for the relative speed. If I would use the speed in RPM, then it would be for each motor, it would be a little bit different depending on the nominal speed of the motor, on the design, on the number of poles. So it's more general and easier to use the relative speed. Sometimes those figures are also shown as a function of slip. Slip is kind of inverse proportional to the speed. So when we have standstill, speed 0, then the slip is 1, so we have the maximum slip. And as the motor accelerates and comes closer to the synchronous speed, then the slip is reducing. At the synchronous speed, the slip would be 0, because the motor would run synchronously in synchronism, so there would be no slip. Of course, asynchronous motor always operates with certain slip. That's the principle of the motor. Now, understanding the wave shape of the torque, why it looks as it looks, is very important to understand the performance of the direct online motor first. Why the stator current is so high at the beginning, at the start. And when understanding this, we will also understand better how the VFD operates the motor and what is the advantage of the VFD. Like the possibility to have the nominal torque from 0 speed without having this high starting current. So this is one of the key advantages of the VFD. Understanding this shape of the torque is not so complicated. You can see those formulas, but actually to understand it, you don't need any heavy mathematics, you don't need any complicated calculations. It's sufficient if you understand basics of physics, and if you can analyze very simple electrical circuit, just with inductance and resistance, and you understand the principle of induced voltage. That's all you need. With that knowledge, I can explain to you, or let's say analyze this torque wave shape, how the torque is produced. So this is what I will be showing you.